way back in general chemistry, you learned 3 definitions or 3 categories for acid-base reactions. You looked at the Arrhenius definition, where you had a proton donor and a proton acceptor in water. You learned the Bronsted-Lowry definition, where you had just a proton donor and acceptor that could be in any solution. And then you learned about Lewis, which was all about electrons donating and accepting. In organic chemistry, we don't care about all that. We're looking for just the gist of it. So if I look at an acid and I'm thinking about something that is going to accept, it's going to donate a proton, or it's going to accept an electron pair, think about what this tells you as a whole, right? What kind of molecule will donate? The positive is specifically a proton. The proton and the electron together make up a hydrogen, and therefore that proton can also be that hydrogen transfer that you see in a lot of the mechanisms. For something to give off a positive, it's going to start out positive or partially positive. For something to accept an electron pair, that negativity is attracted to a positive or partially positive. So the big picture category that we're looking at here is an acid is something positive or partially positive in comparison to whatever it is that it's reacting with. If we look at a base, we talked about an OH minus in solution. I think I gave it to you wrong when I said Arrhenius definition. It's an OH minus in solution, which would accept a proton. Bronsted-Lowry is just anything that accepts a proton. And so if we're talking about something that accepts an H plus or something positive, a proton, the charge would be negative or partially negative. If it's an electron pair donor for the Bronsted-Lowry definition, that electron pair is negative or partially negative. And so when we're looking at acid-base reactions, we're looking for something negative or partially negative compared to the thing that it's reacting with. And you have seen this very, very early, not just your acid-base reactions, but in the early mechanisms. For example, if you had an alkene and you were told to react it with something like H2SO4. H2SO4 is a large, lots of atoms. We don't care about any of that. It's a source of protons in solution. We have H2O as the implied solvent. And in this case, it's not so much a reagent that reacts with a molecule. It's an acid catalyzed reaction. So with acids and bases, if you can identify that we're adding a source of protons or a source of negativity in solution, then you can see where the reaction is going to go. The acid here is just about giving us the carbocation intermediate, and then the water is the thing that reacts. That's the next step. But we want to recognize we have a proton donor in solution. If I take a molecule with a halogen on it, for example, a chlorine, and I'm reacting it with H2O again, but this time I'm putting it in a solution of NaOH. When you see that NaOH and recognize that you have a positive spectator, get rid of it. If I see that Na plus positive spectator, get rid of it, it tells me whatever's next to it is negative, and that is going to give me a base catalyzed reaction. That is the base, and in this case, it would be an E2 reaction, but recognize that it's the OH minus that does the reaction you studied. In this case, E2 will go with the Zaitsev product, the more substituted pi bond. But you don't have to memorize these specific reagents. You can look at what else looks like it. Even if you don't recognize it, it should react in a similar way. I gave you H2SO4. I could just as easily have substituted in something like HCl or HBr. HCl is a strong acid. HBr is a strong acid. If you didn't know that, look for the pattern. You see something that you don't know what to do with, but it's got that H. That H is a proton donor. If this is a molecule that could react with a proton, that is another form of the acid catalyzed reaction. If I look at that base, I have NaOH, but what I really had was an Na plus positive spectator, and an OH minus, my base in solution. If that's the case, then I can swap it out for something else. I can get an OCH3, or this is sometimes written with the Me for the methyl group, an OMe, negative charge. I can have an OET, which is an ethyl group. I can have an O with a tert-butyl group, a tert-butoxide. The thing you want to look at here is the pattern. I have an O, I have the thing attached to it. I have the negative charge. How does that react? And where do I go from there? Brian, thank you so much. I really appreciate it. Thank you so much for stopping by to share that. And thank you for the sending the strength to crush it, because for the students in it is definitely a difficult class, but we can do this, right? We are getting through this together. You are going to see acid-base reactions show up all throughout organic chemistry 2 with the more advanced reactions. If you have something that looks like this, I think someone said they had an epoxide exam coming up soon. I can choose to react this molecule. Let's move this over. I can choose to react it in conditions that are acidic or basic. So let's say I choose to use something like an NaOCH3 in a CH3OH, or just a CH3OH, but let's put that on the bottom as the solvent. And then maybe I'm choosing to put something like H2SO4. Recognize the acid, recognize the base, and consider that even though you have a completely different reaction, we're looking at an epoxide here, how does having a familiar acid or a familiar base impact it? Positive spectator, that right there is my negative. Negative can do a direct attack. That can attack just like an SN2 reaction. Positive, that's a source of protons in solution. How will something like this react? How does an alcohol, or in this case an ether, react with acid? It attacks the acid. So if you're starting to get the idea, if you're starting to see how these patterns will show you a new molecule, similar reaction to something I know, let me see some fire emojis in the comments. Also, if you are just joining, welcome. Don't worry about copying everything down. I've got you covered. Just put live notes in the comments, and I'll drop a link for tonight's session notes. Yes, even if you're watching the recording. So let's move on to the next category. I was using acid and base as a warm-up, but the one that you spend a lot of time on in organic chemistry 2 especially, but some students will learn it in Orga 1, is oxidation and reduction. Now, if you learned this topic in general chemistry, you learned about it from the perspective of electrons. You learned about it with electrolysis and the battery and all those crazy equations. We don't care about any of that. The mnemonic that I like best, especially in organic chemistry, is looking at Leo the lion says, grrr. That was my scary lion roar. And what Leo the lion says grrr stands for is loss of electrons, oxidation, and gain of electrons, reduction. But organic chemistry, you constantly see the movement of electrons. What does this actually tell us? How does this help us? When we think of an electron and a proton together, think of the atom that it makes. An electron and a proton together gives us a hydrogen atom. And so the way I want you to think of it in organic chemistry is if you lose a hydrogen, you get oxidation. If you gain a hydrogen, you get reduction. Now, oxygen and hydrogen are typically the inverse of each other. When you break a bond to oxygen, you typically add hydrogen. When you break a bond to oxygen, I remember what I said. If you gain or lose a hydrogen, then oxygen is typically the opposite of that, which I'll show you in a moment. But the way you can translate that is if oxygen and hydrogen are opposite, then the loss of a hydrogen oxidation also tells us that the gain of an oxygen is also oxidation. If the gain of a hydrogen is reduction, then the loss of an oxygen is also reduction. So oxidation, gaining oxygen. Reduction is not gaining oxygen. That was all very, very hypothetical. So let's take a look at one class of reactions that you will be using a lot this semester. If I take a primary alcohol, and I'll put my O and my H, this primary alcohol, the carbon holding the oxygen also has 2 hydrogen atoms. If I make this undergo 1 round of oxidation, I'll just put O in brackets to show oxidation, then the first oxidized product I get is my oxygen is here, but I no longer have the hydrogen. I'm losing 1 hydrogen atom, so loss of hydrogen is oxidation. And what I'm gaining is not an oxygen atom, it's a bond to oxygen. So the bond to oxygen gives me that bond right there. I still have hydrogen, so I want to do a quick accounting of what happened. Bonds, not atoms. I had, this carbon had 1 bond to oxygen and 2 bonds to hydrogen. It now has 2 bonds to oxygen, 1 bond to hydrogen. So notice, and I crossed out this because the oxygen also has to lose a hydrogen, but the carbon that got oxidized lost a hydrogen, gained an oxygen, all in the same reaction. It couldn't gain one without losing the other. And so that is how I think of that oxidation reaction. And we're going to need a little more room. I can oxidize this one more time for a full oxidation. And that will give me my carbon skeleton. I have my initial bond to oxygen, the second bond to oxygen, which I showed in red. And let's add another pink bond to a new oxygen that is added. And then we have a hydrogen on that. So watch what happened. This carbon right here got oxidized. What happened? It had 2 bonds to oxygen, 1 bond to hydrogen. And now it has 3 bonds to oxygen, 0 bonds to hydrogen. The hydrogen here is sitting on a different atom, not on carbon. So it lost the hydrogen, gained an oxygen. That is the idea of oxidation. Oxidation, gaining bonds to oxygen, got oxidized. That O is in every part of the word that we said. And so if we're looking at the reagents that can carry out this reaction, I don't want to see sodium borohydride or lithium aluminum hydride. Think of what is happening. To add oxygen, we're going to need oxygen. And so we're looking at a reagent that has, well, oxygen. That is where the pattern for this. That is how you're going to recognize your oxidizing reagents. And some examples for oxidation reagents are, look at what I can draw here. OSO4, it's got the oxygen. KMNO4, KMNO4, again, oxygen. O3, these are not all for this set of oxidation reactions. That's just oxidation in general. O3 has oxygen. Then we get something like PCC. I don't really see the oxygen there, but if you look up the structure for PCC, it's pyridinium chlorochromate, and that chromate has a lot of oxygen. PCC is the cousin of Na2Cr2O7. That's the chromium, and that has more oxygen. That is a lot of different oxidation reagents that will give us oxidation. Now, for these specifically, you do have to learn some nuances, but the patterns will help you make it easier to remember. To go from just an alcohol to an aldehyde, I did not put any names on here, so let's do that. We have a primary alcohol. We have a partially oxidized aldehyde and a fully oxidized carboxylic acid. So most oxidizing reagents are way too strong, and they are not going to stop at the aldehyde. They're going to go all the way to the carboxylic acid. To stop at the aldehyde, we need to use a special oxidizing reagent, PCC. This is a weakened reagent. It's not strong enough. And the way I remember it, this came from one of my students, PCC, it starts with a P. It's a prude, doesn't go all the way. It stops. And then if I want to go all the way, I can use any stronger oxidation reagent like KMNO4, Na2Cr2O7. Just make sure if you're using something in base, you then add an acid to it so that you can protonate and not get the carboxylate. If I want to reverse this reaction, if I want to go from a carboxylic acid to an aldehyde or to an alcohol, what I am doing here is the reverse of oxidation. That would be reduction. If oxidation involves oxygen, reduction, we said, is going to involve hydrogen. It breaks the oxygen bonds. It adds the hydrogen bonds. And so we'll want to use reagents that have a lot of hydrogen. What reagents have a lot of hydrogen? We can use, I'll put them, I don't even have where to put them. We'll put them here. LAH, which is lithium aluminum hydride. This is both of them are the correct way to draw it. Sodium borohydride is the other very common one that you are going to see. And notice we have hydrogen, hydrogen. You'll sometimes see just sodium hydride, NaH. That's got more hydrogen. There's another wonky one. If I tell you react an aldehyde with, or not necessarily an aldehyde, but react this molecule that looks like it could be reduced with something that looks like this. That should be capital BALH. Sometimes that H is drawn with a dash. Dibal. Oh, dibal's got a hydrogen. That is probably going to do a reduction reaction because it has that hydrogen. Now, I have shown you a lot of the common reagents that you're going to see. And these are the ones that you'll typically expect on your exams. But you might see something that looks like this, where, let's see what we have here. We have, this is a screenshot taken out of the reagent guide by James from Master Organic Chemistry. And the reagent guide is really, really useful as you get more and more advanced in organic chemistry, because especially now when everyone turns to AI for help, AI makes mistakes, AI is confused, AI will often give you the wrong answers. But this guide was created by a PhD in chemistry who took ages to research and look up every single reagent in the text and the research where they figured out exactly what it does. And so he's got all the information laid out for you. If you go to leahforsci.com/guide, scroll down to the bottom of the page, that's where you will find a link to purchase the guide. In the comments, put referred by Leah for Sci, and he will give you a 15% discount. That is a special discount for my subscribers, for my followers. So for example, from a long list that he had for redox, he's showing you different kinds of reactions. I've already shown you some of them, going from an aldehyde to a carboxylic acid, alcohol to a carboxylic acid. He's showing you the oxygens that are changing, right? So we have oxygen, 2 oxygens. We can clearly see that's oxidation. Alcohol to carboxylic acid, again, he's showing you very clearly what is happening. But then let's say you see a reaction that looks like this. You don't necessarily recognize it based on what we just saw, but hey, we are taking a carbon that has just hydrogen and we're turning it into a carboxylic acid. That is oxidation. So he's showing you all the different reactions with the right reagent. Then you have other classes of redox that aren't necessarily with oxygen or with just going from alcohol to aldehyde and so on. So here's a couple more he shows on the guide. From an alkene, oxidative cleavage. Notice that you cut it in half, you add the oxygen, you get a reagent with oxygen. Going all the way to a carboxylic acid, again, a reagent with oxygen. So he's got the list, the overview of the reagents, but then what I really like about this guide is that he also goes into more detail. So for example, chromic acid, I kind of mentioned it before. I showed you the cousin of chromic acid. You get a complete breakdown. So here's what it looks like. You have the name, the formula, what it actually looks like. And then he's got a lot of relevant and just helpful information as you're studying. If you get stuck, if AI is driving you crazy, just open the guide, look it up. He's got a lot of examples. This list just kept going, but I didn't want to take a massive screenshot. So he's got example 1, example 2, and so on. I highly, highly recommend this guide. layerforsci.com/guide. Scroll down for the link and let him know in the comments that I sent you. All right, so as you're going through these reagents, and we'll do more examples in a moment, and you're thinking, oh my goodness, there is so much here to memorize. The good news is that when you study it the right way, it will be a lot easier. And by the right way, I mean step 1, make sure you understand, because you'll still have to memorize. But when you're looking at a reagent and just saying, this is what it is, this is what it does, this is what it is, this is what it does, that's too much information. But if you're looking at the reagent the way that we just did, and you're saying, okay, so there's a negative oxygen, it's similar to that other negative oxygen. A negative will attack at the less substituted side because it's going for that direct attack. If you look for the patterns, then you will have a much, much easier time remembering what is happening. So patterns and logic, that is your top priority when you're learning. And once you understand, only once you understand, then you go to step 2, and that is to memorize. There are many, many different ways to memorize. I don't like flashcards. I think flashcards are too passive. They teach you regurgitation, and they don't teach you to think. They don't take the understanding into your long-term memory. So when you are memorizing, use an active method so that you actually get to learn and process. I like to use, and I teach what is called active memorization. I'm dropping a link in the YouTube comments. Active memorization is not just flashcards. It's writing it out, drawing a reaction, drawing the reaction in a different way, adding a different molecule, and I give you examples there. If you can do it this way with the patterns with the mnemonics, you're actually going to get it and therefore remember it in a way that actually sticks. And of course, you want to repeat. I would much rather see you do 15 minutes a day for 4 days in a row, or 15 minutes in the morning, in the afternoon, at night, rather than just sitting for an hour, because there's a capacity to how much your brain will absorb at once. And the way I think of this is, I'm very thirsty. Let me get a cup of water. But that cup isn't big enough. I'm still thirsty. Let me pour more and more and more. That water is not going anywhere. You drink, you let it sink in, then you have some more, then you have some more. So let's do some more practice with this to see. For example, if I take a molecule that looks like this, I have an alkyne, which is a carbon-to-carbon triple bond right over here. I can react this with 3 different reagents to get 3 different reduction products, because I can reduce this partially or all the way. If I react it with H2 and something like a palladium carbide catalyst, just H2 and metal, then I'm going to get a complete reduction where every pi bond is broken. Notice there are no oxygens here, but the pi bond is a carbon-to-carbon bond, now turns into carbon to hydrogen and another carbon to hydrogen. This is a double reduction. Each carbon is reduced twice, once per pi bond. But if I react this with a less reactive hydrogen, for example, H2, let me change the color, If I react it with H2 and something like a Lindlar's catalyst, this is also going to add hydrogen, breaking the pi bond, but it's not going to break both of the pi bonds. It just breaks one pi and therefore gives me only one hydrogen per carbon. Now, what is happening here is that I have the Lindlar's catalyst is like a poison metal catalyst. It holds on to the carbons that it holds on to the entire molecule, and the hydrogens kind of slide in where the metal is holding it in place. That's in general how metal reduction works. But in this case, the Lindlar's catalyst is holding it in a way that only lets one hydrogen add per pi bond that is broken or per side. And that's why you stop at the cis alkene. So this is not memorize Lindlar's, I get cis. It's understand why the hydrogen slides in from the same side. Lindlar's doesn't let it go all the way. If, however, I react it with what looks like a metal, because it is in all the way on the left of the periodic table, something like sodium or lithium in liquid ammonia. In this case, this is called dissolving metal reduction, and I still get one of the pi bonds broken, not two, but this one gives me a trans alkene. So again, it's a reduction, something's happening with reduction, but why does it go trans? First, I want you to notice that the way I drew the sodium, I drew a radical there even though you don't have to. That is to remind you that that is a neutral radical sodium. Neutral and radical. It's very, very reactive, not like your sodium positive spectator. And so that will give me a radical intermediate. There will be radicals on the other side, and they want to go as far away from each other as possible. That is why we get trans. So this is a reduction where we're not looking at hydrogen atoms. It's a reduction where we're looking at electrons. Same idea, really, but it gives us a completely different outcome. Let me know if that is clear and if you're with me so far. Let's go back. I know I put a list somewhere. Where did I put the list? Okay. So we talked about acid-base, oxidation, and reduction. The next category that a lot of the reactions will fall into is a carbon-to-carbon bond formation. Typically, this is considered chain elongation, but sometimes you also have that as ring formation. And so what we want to see is what is going on here with the different kinds of reagents that we can use. In Organic Chemistry 1, you learn about the acetylide anion. You have an alkyne with a terminal negative charge, a deprotonated alkyne, that can act as a nucleophile for an SN2 reaction. And so if I have a carbon chain that looks like this with a chlorine, that's the SN2 that can happen. That will give me my carbon chain, a new bond here. And then let me actually put the new bond here so it fits on the page. And then there's the alkyne that added. So notice I formed a longer carbon chain, merging the green and the blue. So you'll see your alkynes. You'll see your organometallics like a Grignard, organolithium, Gilman reagents. These are all they look very different. They look kind of scary, but they don't have to be. So let's see what about these reagents makes them reactive. What makes them work? For this one right here, you'll either start with the alkyne where you'll deprotonate, or you'll see it written as something like Na and then CCCH3. That's your CC triple bond, and then that's the CH3 right there at the end. The Na is a positive spectator. It looks like a metal sitting next to the atom. If you're looking at your organometallics, you may see something like, let's put something like, have an acetone reacting with something like that. MgBr. That would be your Grignard. And let's do a couple more just to show you first, and then we'll go into the reactions. Let me move that down. Just give you a couple of examples first. So for the Grignard, we're looking at an R MgX. So notice we have the R. That's going to be how we get our chain elongation. Attached to the MgX, that's how we know it's a Grignard. If I have something slightly similar, let's say R2CuLi is the way that it's generalized, R2CuLi. This one right here is your Gilman, and then we already looked at the alkyne. We'll just use these two as the example. Notice again, we have R2, but only one of them is going to add, and it's attached to a CuLi. A Cu, we have the Li, an Mg, an Na. The key here is if we have carbon doing the attack, that carbon is going to act as a nucleophile. That is what drives your chain elongation reactions when the carbon does the attack. So a carbon nucleophile, well, first let's break it down to see what a nucleophile is. Nucleophile, that means nucleus loving. The nucleus is positive, and something that loves positive is going to seek positive, positive seeking. What kind of atom or molecule is looking to react with something positive? A nucleophile is negative or partially negative. So what makes these carbon atoms negative or partially negative? We have a carbon bound to a metal. If that metal is positive, partially positive, I am seeing comments in a language I do not understand. So you're going to have to translate that to English. Otherwise, I don't understand. What makes it reactive? We have the carbon near a partially positive Grignard, a partially positive copper lithium, a positive, not partially, a full-on positive sodium. This is not as reactive because of the positive charge. This is more aggravated by being still bound to that atom. And so if you can recognize what it is, it's positive seeking. We're looking for something negative or partially negative. Then when we look at the reactions, even if you're not completely familiar with the reagent, you can kind of still figure out what it's going to do. We have a bond right here, but that carbon, whoops, I missed. That carbon will attack the partially positive carbonyl carbon, kicking that out. That will give me the oxygen here, a new bond to the ethyl group, and then we do protonate it. Step 1, step 2, we'll put an H+, so that goes right there. So that was one type of chain elongation. For students studying epoxide reactions, it works the same way. If I react this with a Grignard, for example, a CH3 MgCl, it'll attack at the easiest, least sterically hindered side. And then kick that up. That's step 1. Step 2, we add an H+. The H+ goes here. We formed a new bond, and look, very similar reaction, very different class of reaction, but we still get the product there. We still get that chain elongation, and typically we do have to protonate. All right, I see a very impatient student here. Wow. Oh my God. Oh, guys, I do try to answer all the comments and all the questions, but let's take a breather. Okay. Although I do appreciate how excited you are to get the notes. So you're looking at something like this, and I can keep going, right? Grignards will do so many different things. You see something like this. These are reagents that you recognize. What if I then give you a reaction where I throw in a PHLI? Maybe you've never seen this reagent before, you don't know what to do. Just take a step back and ask yourself, what do I see? pH is a phenyl group. That's benzene as a substituent bound to an Li. Well, wait a minute. That carbon is bound to a metal. That right there is a carbon nucleophile. That is likely going to attack something and add phenyl group onto something else. So you're looking at, what does it do? What does it remind me of? And then considering, well, what can I do with it? So this is another screenshot that I grabbed from the reagent guide. Again, this is the guide from Master Organic Chemistry. It's highly recommended resource when you're learning so many reactions and reagents, especially because AI likes to make mistakes. This is going to give you exactly what the reagents are, what they do, no confusion, no second guessing. And you can take a screenshot to the AI and say, no, show me how to use this right here with the right explanation. Because my students use AI, I'm experimenting to see what they are seeing so I know how to help them. And the amount of times I have to say, no, ChatGPT, you are wrong. This is, anyway. So I will just grab this and say, here's the evidence. Use this to answer the question. And it'll still get it wrong half the time. So if you go to leah4sci.com/guide, you'll see a link there. If you get the guide, just put referred by Leah for Sci. He's going to give you a 15% discount. That is a special deal that he has for my subscribers. And so, for example, with organolithium reagents, so this is what you can expect for all the different reactions in the guide. You have an overview of the reagent. You have the general format, RLI, and a specific example. Then he's showing you, so what is it used for? It's an extremely good nucleophile, reacts with electrophile, gives you an overview of the different classes. Wow, I keep crossing it out instead of underlining. And then he's also helping you make connections. So this isn't just rote memorization. This is, hey, let me understand. It's very similar to Grignard's. And here are some examples. Now, as you're going through the guide and studying the examples, don't just look at them and memorize them. Make sure you understand. Okay, so I take this alkyl halide, I react it with 2 lithiums, and I get this right here. And if I have this right here, that's the same idea. So can I reverse engineer and say, oh, if I had bromine here and reacted it, I could have done the same reaction. This is a good way to create practice, to get really comfortable with just, this is what I know, let me practice it in this format, example 3, example 4, and just keep drilling in the context of reactions so that it makes sense, as opposed to just memorize, hope you remember, and then you kind of blank out on the exam. So this is just another example from the guide, and obviously the guide just keeps going. I mean, that thing is, I don't even remember how many pages, but it's dozens and dozens and dozens, and highly recommend. All right, so let's move on to halogen and functional group delivery. So with halogens, these are really critical when we are doing synthesis, because if I want to put a functional group on the molecule and I have a halogen, I can do substitution, I can do elimination, and I can go anywhere from there. All right, so let me see. Question, when should we protonate? Okay, so I assume you asked that earlier and I didn't see the question. With something like a Grignard, I think that's where you're asking. Make sure that it's in the second step. Because if you take your reagent and you pour in some acetone, you pour in some Grignard, you pour in some acid, the protonation, you put it all into one container and shake it out, you're not necessarily going to have this reacting in steps. The Grignard is very lazily going to grab that proton, destroy the Grignard, the reaction is done. So first you want to do step 1. Make sure that reaction goes to as much as you can to completion. Then when you know that all the Grignard is reacted or you've given it enough time to react, then you add your acid so that The Grignards are no longer active as Grignards. Now we just have a lot of these with O-. Then you start to protonate. Let me know if that is clear. Why is K2Cr2O7 a good oxidizing reagent? So for that, you have to look into the reactivity of it. So the K2, let me go back. We are going, where were we with redox? Over here. I'll just squeeze it in down here. So you're looking at K2Cr2O7. That is really just Cr2O7 with a 2-. That K2, that's a positive spectator. And then if you look at the structure of how the oxygen sits on the chromium and how that reacts with molecules that you bring it next to, if a molecule is going to react, that makes it a strong reactant. And if the reaction is an oxidation, then that is a strong oxidizing reagent. So Cr2O7 is very reactive when you bring it next to, say, alcohols or aldehydes or things like that, making it a strong oxidizing reagent. And guys, you don't have to post the same question 10 times. If I see one, I see them all, but I don't look at the chat the entire time. AI never helps me with any orgo. AI, I have a love-hate relationship with it. My stance on it is, even though it's not necessarily helpful and it is exhausting and it drives you crazy, it is going to be what people use in the future. And so I just remind myself that when smartphones came out, yes, there was a time before smartphones. There were people who kept fighting it, and ultimately smartphones became the thing. When cars came out, there were people who were fighting it, sticking to their horses. So you do have to evolve with technology. But right now in your orgo semester, you still, well, first of all, even if it is helpful, you don't want to use it as a crutch, because when you get tested, you cannot use AI on your exam. You are asked to rely on your brain. You are asked to think. You are asked to show what you know and understand. That is what you're getting tested on. And so if you get comfortable relying on AI to give you answers, if you outsource your thinking, your brain is going to stop working, right? If you don't challenge it, it's not going to work. You are very welcome. And that just means you will struggle on exams. And so whether or not you like AI, whether or not you find it frustrating, you want to make sure that you can perform on exams without AI based on learning, understanding, memorizing in context, memorizing with patterns, memorizing with things that make sense, so that you can do well regardless of what is happening with AI. And that's why I recommend something like the Reagent Guide. That is the learning way to get answers. All right, so then let me know if I answered your question. Also, if you are joining late, welcome. Don't worry, the recording will be live on my YouTube channel even when I'm done. And if you missed the beginning, you can catch up, and don't worry about taking notes. I've got you covered. Just put live notes in the comments. Yes, even if you're watching the recording, and I will send you the link to download the notes. And the reagent guide that I keep referencing, go to leahforsyth.com/guide. I'm also putting that in the comments. Put referred by Leah Forsyth in the comments, in the notes to seller, and he'll give you a 15% refund. That is a special deal that I worked out for my subscribers. So let's move on to halogens. We talked about why they're so important. If you watched my synthesis session, one of the patterns that I talk about is the something from nothing. If I want to take this right here and I want to turn it into a molecule that looks like this, for example, and I want to put whatever else on it, there is nothing I can do before I get something reactive on this molecule. I can't attack it. I can't eliminate. I can't connect. I can't elongate. I need to put something there. And halogens will be your go-to. So you can put halogens on all sorts of molecules. This pattern, I call this something from nothing. That is one type of method to get a halogen on there. And so when we're looking at adding a halogen, we're thinking, I want a halogen on there. Let's use something like bromine as an example. There are so many reagents. I can use HBr. I can use Br2. I can use NBS. Where do you even go with this? Look at the reagent to understand why you use one or the other in any given situation. So let's say I'm starting with a molecule that looks like this. I have a pi bond, and I'm reacting it with, well, let's go with all three to understand the context. So to react it with all three, I'm going to need that on the clipboard like this. Okay. To react it with all three, let's start first with HBr. We're not memorizing the difference. That's key. We're understanding the difference. If I react it with HBr, which you should recognize and remember, this is an acid. How do I know it's an acid? It's got that acidic proton. Acidic protons will break pi bonds, and if I have two things to add, when I break a pi bond, I have two carbons that need something added to them. And so the two things that I can add would be a hydrogen and a bromine, because that's what I have available. Hydrogen goes less substituted, bromine more substituted. That's following Markov-Combs rule. The hydrogen is not visible in line structure, so technically it looks like I just added a bromine. But the logical memorization here is I had an H, I had a Br, I added both. If, on the other hand, I'm choosing to react this with Br2, then the same logic applies. I broke a pi bond. I'm adding two things across the pi bond. And if I have Br2, then the two things that I have available are bromine and bromine. That's the logic behind this reagent. The least common one, the scariest one, and if you're taking the ACS, let me know in the comments, because you absolutely have to know what this stands for and what this means. If I use something like NBS, that pi bond is not going to break, but I will get a bromine adding on the side next to it. For example, I can get a bromine here, or I can get a bromine here. I can even get a bromine here. Okay, so what is going on here? How can we logically understand what is happening? For my ACS students, NBS is N-bromosuccinimide. And the way I think of this reagent is that it's a bromine babysitter. So that molecule, N-bromosuccinimide, is a succinimide where the N has a bromine. This is protecting the bromine, controlling it in the process of creating radicals. It's a radical and bromine babysitter. That radical will form on a carbon that is next to a pi bond so that the radical can resonate. And then it'll give up the bromine where that radical is and put it on there. So if you recognize it babysits the bromine, it babysits the radical, and it puts it on a carbon that is going to have been stable to the radical, that will help you remember where that goes. Radicals, we kind of talked about radicals over here without actually specifying. And so if you have nothing on the molecule, then you want to use something like Br2 with peroxides, heat, or light. Basically anything that is going to, let me move this to the side, anything that is going to break up the bromine. So in the first step, we have Br2, peroxides, heat, light. And what this will give you is just one halogen. There's a couple of different peroxide reactions to put a bromine on, but we'll just use this one for now. It'll give you one halogen. And the idea is that you're using something to separate the two atoms in a way that makes them so excited and so unstable that you get a radical intermediate, and then all the radical steps. I'm just going to put a bunch of arrows because that synthesis, how would I do this? For students who are actively learning this, this is your challenge for homework. I would turn this into a Grignard, make 2 of them, and then attack something like a, what would I get? A formic ester is probably the way to do that. And then oxidize it again. Fun reaction to try on, for homework. All right, so we saw this. We kind of have an idea of what is happening. And then your professor decides to hit you with an SOCl2, a PBr3, a tosyl chloride. Okay, so what is happening here? These are all reagents that seem to have nothing to do with each other, except there's a halogen, there's our halogen, there's our halogen. And if you draw them out, especially the ones that are easier to draw, you'll see that I have a central atom that can get attacked, like my sulfur, like my phosphorus. The tosyl chloride, you do have to know what it is. You can't just invent it. But even if you forgot, you can still say, oh yeah, it's got a chlorine. So ACS students, you do have to know the tosyl chloride is toluene sulfonyl chloride. That is toluene sulfonyl chloride. So let's say you learned this reaction, you studied it, you memorized it, you recognize that ultimately it's about having a big molecule that will stabilize the atom, for example, turning an alcohol into a good leaving group, and chlorine comes off. You memorize this, you understand, you get to your exam, and you see a mesyl chloride. And you're thinking, mesyl chloride? I've never learned that. But wait a minute. It kind of looks like a funky word with a chlorine next to it. You know what? I'm just going to treat it the same way, and you will get that question right. Because it's basically the same thing. Just instead of a tosylate, it's got a mesylate, and the rest does pretty much the same thing. So we looked at alkenes. But even with something like this, we can take the HBr and we can say react it with just regular inert solvent like CCl4. We get this one right here. But if I took that HBr and I reacted it with, I'll just put it in a box to separate. If I reacted it with HBr and peroxides, that box does not fit. Let's see if we can squeeze in the molecule. I would get something that looks like this, but the bromine would go on the end. The peroxides give me a radical intermediate, and the radical changes the stability of the intermediate. Therefore, it changes the outcome. Memorization, yes, but memorization with logic so that you can make it easier. So what's the best way to explain that? If I have to memorize 100 things as 100 random facts, I could do it, but it's going to be very, very difficult. If, however, I have to memorize 100 things that are kind of connected, that makes sense. Now it's not 100 random facts, it's 10 groups of facts with, say, 10 things in it. That makes it so much easier. Looking at the questions, that makes it so much easier because now I don't feel like there's 100 random things I have to know. So for example, here, how many reagents did we just look at? We have HBr, no peroxides, HBr peroxides, Br2. We have NBS, right? These are a couple of different reagents, but if you can study them together and look at the logic, then you say, okay, in this condition, this is why it goes that way. In this condition, that is why it goes that way. SOCl2, PBr3, tosyl chloride, mesyl chloride, a triplet. If you see them written out, you suddenly don't have 50 reagents to memorize. You just break it up. So if that makes sense, and if you see yourself having an easier time studying reagents as a result, which was the goal for today, right? I can't just make the memorization vanish, but hopefully I can make it easier to understand. Let me know in the comments. I did not see when you wrote that. So if you can just clarify what you want me to repeat, I'll be happy to. 12th board, good luck. Taking the ACS, so you do have to know all that. Another ACS. ACS students, email me. I have a guide for you. Oh, I'm so happy. That is my goal, to take these scary topics and break it down. So the fact that you wrote that, I'm so happy to see that, because that is my mission. And hopefully also learning to love the material. Thionyl chloride. Okay, so thionyl something, chloride, probably a chlorine, a halogen delivery system. We went through the categories and we looked at some examples. My goal for the examples I showed you today was not to teach you all the reagents, because that obviously would take too long. What I was trying to do is show you how to categorize, how to group them. But now that's where the real homework begins. So what you want to do using the active writing method is you want to run drills. That's supposed to be a D, not a P. And the way that you run drills is you create your own practice example where you're going to vary the reagent, the reactant, and I'll show you what I mean. You can add symmetry or take away the symmetry. You can change the degree of substitution. You can use rings to make it scarier, because somehow professors love scaring you with rings. You can change the functional group, FG for functional group, and on and on and on. So what do I mean by that? We talked about alcohol oxidation, and we'll use that as an example. And I gave you this molecule, and I turned it into an aldehyde and a carboxylic acid. If you are practicing your oxidizing reagents, take this one and just draw it out with reagent 1, reagent 2, reagent 3. What happens if I use a potassium permanganate, a sodium dichromate, a different version of chromate, PACC, which also has that chromium in it? If you get comfortable with the reagents, make sure that your professor is not going to catch you off guard. So you want to change it up. You want to turn it into a ring. You want to change the substitution. So that ring is actually secondary. I could turn that into primary. I can turn that into tertiary. And just practice what happens in each case. Tertiary obviously will not get oxidized because this carbon has too many bonds to a carbon. We have no hydrogen. So let me make sure I showed you all the ones. We changed the reagent. You just practice all the different ones. You change the reactant. I give you different alcohols. Symmetry or asymmetry, if you want to. For molecules where symmetry makes a difference, that matters. So for example, if you're practicing your alkyne reduction, something like this versus something like this versus something like this. These will give you repetitive practice that is not the same. And if you do it over and over in this active format, we do this one and this one and this one, your brain will get so comfortable with the pattern. The pattern is anytime I see that, I know what to do, no matter how you change it up. So that is your homework. That is what I want you to do from here. With any new reagent or reagent class that you see, and I guarantee you will feel so much better, so much stronger, and so much more confident as a result.